Okay, so we're just wrapping up that last example that we were in the middle of in the last video, and then we're going to be done with section 8.1. So just a quick recap, we were working on a linear system where it was a non-homogeneous system, and we were given a general solution. We were being asked to show that it was a general solution, and we're using this theorem up here. So we're looking for a complementary solution and a particular solution which are given in the form of this general solution. What we did in the last video is we showed that the first of these two, this thing that we're going to call x1 here, does in fact work as a solution to the system up here. And then we said you could do the same thing with x2, but because it's so similar looking, it's not really worth the time to go through all of those steps again. So I'm encouraging you to go check that yourself. Now what we need to do is show that these two solutions form a fundamental set of solutions. So this is a 2x2 system, which means we need two solutions in order for this to have the potential of being a fundamental set of solutions. We already have those. Now we need to show that they're linearly independent, and that's where the Wronskian comes into play. So I'm going to evaluate the Wronskian of x1 and x2 next. Okay. Now we have x1 and x2 given up here. I'm going to multiply the exponential functions into those for the purpose of evaluating this determinant. So that's going to look like this. Remember, the first column is x1. So x1, after multiplying that exponential function in, is going to look like e to the root 2t, negative e to the root 2t, minus root 2 e to the root 2t. Okay, now up here, if I multiply this exponential function into that matrix and use that as a column here, it's going to look like e to the negative root 2t, negative e to the negative root 2t, plus root 2e to the negative root 2t. Okay, and we did something kind of similar to this before, where we made an observation that helped with the evaluation of this determinant. I just made it go a little bit faster. If I notice here, when I evaluate this determinant, multiplying these entries along the main diagonal, I'm multiplying exponentials of the form e to the root 2t times exponentials of the form e to the negative root 2t. It's happening in both cases. So when I multiply those, root 2t plus negative root 2t is 0. That gives me a 1 every time this exponential multiplies to this. Same thing's going to happen here. This exponential times each of these exponentials are going to produce 1s in those terms. And so keeping that in mind, that's going to make this come out a little bit simpler than it might initially look. So multiplying across the main diagonal, I get negative 1 plus root 2 minus the product along this other diagonal. I'm going to get negative 1 minus root 2. Okay, this is equal to 2 root 2, which is non-zero. So that means this. x1 and x2 are linearly independent, and because we have the correct number of solutions there, we can say that this is a fundamental set of solutions. Okay? So what that tells me is that all linear combinations of those solutions, x1 and x2, so just this part of our solution, form the general solution for the associated homogeneous linear system up here. And that's kind of the first step. That means that we do in fact have a complementary solution here. The next step is to verify that this is a particular solution to the non-homogeneous equation that we were given in the beginning. And all that really amounts to is plugging this in to this system and verifying that it actually works. So what I'm going to do, even though we're writing this as a sum of 3 matrices, I think it's going to be easier if we combine it all into one thing. So notice I could also write xp, my particular solution. If I were to multiply the t squared in, the t in, and then add entry-wise these 3 matrices, I'm going to get 1t squared, so t squared, minus 2t, so that's minus 2t, plus 1 from for my first entry. Then my second entry is going to be 0t squared plus 4t plus 0, which just looks like 4t. Okay? That implies that xp prime, is equal to 2t minus 2 in the first entry, 4 in the second entry. So what I'm going to do is plug this matrix in right here for x, work all of this out, and show that it's equal to the derivative of that, x prime of p. Now I don't have room on this page, so I'm going to jump to another page to do that, but just remember what those matrices look like. Okay, so we're going to do that right here. Let's see. Okay, so the system on the right-hand side had this matrix where it's coefficient matrix, -1, -1, -1, 1, and we're multiplying that by xp, which we just showed looked like this, t squared minus 2t plus 1, 4t. Okay? Plus, now coming back over here, all right, if you look at the original system, we have a sum of these three matrices, which is just a function of t, or technically two functions of t, if you think of the top row as a function of t, the bottom row as a function of t. But kind of like what we did with the particular solution, I can add all of these up into a single matrix just to make the computations a little bit easier. So this will look like 1t squared, or t squared, plus 4t minus 1, and t squared minus 6t plus 5. Okay, so rather than deal with three matrices that I'm adding, I'm going to put them together into one matrix because that'll make the work a little bit cleaner, I think. So let's write that here. We had plus t squared plus 4t minus 1 t squared minus 6t plus 5. Okay, I'm going to do this multiplication first. So if I multiply this column vector to this 2 by 2 matrix, I'm going to have -1 times that first entry, which is going to look like -t squared plus 2t minus 1 plus 4t times the second entry, which would actually look like minus 4t. Okay, then I'm going to multiply for my second row. I'm going to multiply this first entry to this -1 here, which will produce the same terms as before, -t squared plus 2t minus 1, and then 4t times 1, so that's plus 4t, plus this matrix that we had here, t squared plus 4t minus 1, t squared minus 6t plus 5. Okay. Now adding, I see that I have a -t squared and a t squared that cancel, a -4t and a 4t that cancel, so I'm left with 2t minus 1 plus -1, which is 2t minus 2. 2t minus 2. And then for my second entry, -t squareds cancel, 2t plus 4t is 6t, which will cancel with this -6t. That just leaves me with -1 plus 5, which is equal to 4. However, that is exactly what x prime of p was equal to, and that's what we were looking for, because that's going to give me the left-hand side. That's showing that this is, in fact, a solution. So that tells me that this is xp, or x prime of p, which is what we were trying to verify. So now we've done everything we've needed to do. According to this theorem, because we verified that everything on this part of our solution forms the complementary solution, and because we've verified that this is also a particular solution, we know that the sum of those two things forms the general solution for that linear system. Note that we haven't talked about how to come up with either of these. We haven't talked about how we're supposed to find a complementary solution or how we're supposed to find a particular solution. In this example, we were just given those things. But again, this is still mimicking what we did in 4.1 with just single differential equations as opposed to systems. We talked about, a theorem very similar to this one, and it wasn't until the sections that came after that that we talked about, well, given a homogeneous linear system, how do you find a complementary solution? And given a non-homogeneous I think I said system, a homogeneous equation, how do you find a complementary solution? And given a non-homogeneous equation, how do you find a particular solution? We talked about how to use undetermined coefficients, variation of parameters, things like that. So that's what the next 2 sections in Chapter 8 are going to deal with. So that's going to be all that we need to cover in 8.1.